Hi there, and welcome to part 4 of our giant sugar discussion, where we look at really fake sugars, things that don't look anything like our carbohydrates from video 2 or the sugar alcohols from video 3. If you've only got 30 seconds to listen to me, I can summarize pretty much everything in this video in this one tiny little sentence. Most of these fake sugars were discovered completely by accident due to really poor chemistry lab technique, and they don't give you brain tumors or diabetes or cancer. For those of you with more time and the patience to listen to me, come on in. Just to show you where we're headed in this video, there are 7 GRAS, or generally regarded as safe non-nutritive sweeteners, approved for use by the FDA in the United States. There are other ones that aren't on the list we'll mention that are used in other countries, let's say Canada, but for some reason, again, aren't used in the United States. The first 3 on the list here, Aspartame, Neotame, and Advantame, are all pretty similar chemically, so we'll talk about them in one chunk. Then we'll talk about Sucralose, which kind of deserves its own thing. Then we'll talk about Saccharin and Acesulfame K, the K here meaning the element potassium. And finally, we'll finish it out with the new hot kid on the block, Stevia. All that being said, let's start with the first and probably most well-known fake sugar on this list, aspartame. Before we get started on the video, I want to let you know that I'm purposefully steering clear of the wild and very inaccurate misinformation that comes out about these fake sugars on the internet. There's a lot of really bunk garbage that people talk about, and it ruins the chemistry that I hold so near and dear. First and foremost, these videos, me talking to you, are about chemistry. Honest to God, molecules on a whiteboard and things that actually happen. We don't deal in opinions, we deal in facts. Now at the end of the video, if you really want to hear my opinions, I'll get up on the soapbox, and believe me, I'm gonna get up on the soapbox. But at the risk of the entire video devolving into me just batting away these crazy and ludicrous claims from idiots on the internet, we're gonna just push that to the end, okay? This is the molecular structure of aspartame, and as you can see, it looks nothing like any of the carbohydrates or sugar alcohols from the previous videos. The reason is because aspartame is a dipeptide, which means it's more like a protein than it is a traditional carbohydrate. Aspartame is a dipeptide of aspartic acid over here and phenylalanine here. It's created at this bond here, where the carboxylic acid, C double bond OOH from aspartic acid, and that amide group from the phenylalanine, they react, pull out that water, H2O, and the carbon connects to the nitrogen right there. It is also the methyl ester of this dipeptide, so in the bottom right, you can see that this double bond O, OCH3, comes from the carboxylic acid of the phenylalanine, where if you can imagine this being an OH here, and we were to react that with methanol, same thing applies. We take the H2O water, pull that out, tack the CH3 onto the oxygen there, and that gives us the methyl ester of the dipeptide of aspartic acid and phenylalanine. Aspartame was synthesized first in a different purpose like many of these fake sugars, and the chemist James Schlatter tasted his finger and realized it was quite sweet, so that's how it came to be. Aspartame is about 200 times sweeter than sucrose, and it isn't particularly heat stable, so this fake sugar not so good for baking applications. That's why you find it predominantly in things like diet soda pop. One time I was taking out my contacts after I cut a jalapeno and discovered that was a really bad idea. Sometimes you lick your finger and discover the most popular artificial sweetener of all time, and sometimes you burn your eyeball off. Win some and lose some. Aspartame is 200 times sweeter than table sugar sucrose, but we Americans love our sugar, so work was done to put derivatives on aspartame and try to increase the sweetness potency. In US patent 5480668 and substituted derivatives of aspartame useful as sweetening agents, it was found that putting this 3,3-dimethyl-butyl group on the nitrogen here of one of the aspartic acids in that dipeptide of aspartame gave us this molecule, neotame. Now it turns out this group makes it 500 times sweeter than aspartame, which makes it, carry the 3, 10,000 times sweeter than table sugar sucrose. How about that? Other interesting point about neotame, this bulky 3,3-dimethyl-butyl group has sterics enough that the body will not metabolize the phenylalanine part of the neotame molecule. So unlike aspartame, neotame is safe to consume for phenylketonurics, those people that can't have phenylalanine in their systems. Finally, we get to Advantame, because 10,000 times as sweet as sugar wasn't good enough, so we derivatized this nitrogen again Put this group on it with the phenyl and the OH and the ether thing there. And we made Advantame. And this is 20 effing thousand times as sweet as sucrose. So if you really need to get your fix, that's the one for you. Next, we're going to talk about sucralose. And before you bludgeon me to death, I know this is not sucralose. This is regular old table sugar, sucrose. Doesn't it give you the warm fuzzies just to see a traditional carbohydrate again? Before we get to the synthesis of sucralose, which again is from sucrose. You take sucrose, you make sucralose. It's not some like crazy wham bam different molecule going on here. We want to look at the OH groups on the disaccharide of glucose and fructose. Boy, this is all coming back to you now, isn't it? God, I love it. We have the OHs here are secondary alcohols. That means to say they are OH groups connected to a carbon that is connected to two other carbons. Now the other three OHs here are primary alcohols, meaning they are connected to a carbon that is only connected to one other carbon. This becomes important in synthetic reaction chemistry because primary alcohols will react differently than secondary alcohols. It's worth mentioning that this glycosidic linkage in the middle is technically an ether, where it is an oxygen connected to a carbon on both sides, so it will react completely differently from either the primary or secondary alcohols. Same thing applies to the oxygens inside those cyclic monosaccharide structures. Okay? To get from sucrose to sucralose, we want to react the hydroxys here, here, and here. The problem is reagents don't know which things to react with. So, in essence, the primary alcohols here are going to look just the same as this primary alcohol that we do not want to react with. The secondary alcohol is a little bit different. We'll talk about it in a minute. That being said, this third primary hydroxy that we do not want to react like those two has to be called protected. So we're going to do that by an acetylation, where we react the OH group with acetic acid. You come in here, and the mechanism, as you'll see, very familiar at this point because it's the only one I was taught in organic chemistry, called the water lasso mechanism. If you can find water somewhere, H2O, grab it, pluck it out, and then connect the oxygen to the carbon that's left over. So that's the first step in our sucralose synthesis, the acetylation and protection of this primary alcohol. Now that we have our sucrose 6 acetate here, we move to the next step of the sucralose synthesis, the chlorination. If we take reactants like phosphorus pentachloride and trichloroacetonitrile, you can get the chlorination in those three positions you want. So this secondary alcohol over here becomes a chlorine, and those two unprotected primary alcohols also become chlorines. Now you might be saying to yourself, take a look at those secondary alcohols. Why did we only get the one chlorine at the position that we just so happened to want? Honestly, I don't have an answer for it. I looked in the patent and I looked online, and I couldn't really find why that reaction was so selective to this particular position to the exclusion of all other secondary alcohols. If you're a PhD synthetic organic chemist, please comment on the video and let me know why this one's so selective. Certainly from the primary alcohol side, we had to protect this one, or otherwise those reagents would have gone ahead and chlorinated that one as well, which obviously we didn't want to do. So second step of that sucralose synthesis, we go from the sucrose 6 acetate to the chlorinated but still protected product. And now we come to our final step in the synthesis, the deacetylation of the previously protected primary alcohol. And we do that by reacting it with methanol and potassium hydroxide as a catalyst, in the temperature range 40 to 50 C, in the pH range 10 to 11. It's a fairly tight pH range, and the patent says that the pH can be adjusted. No, I didn't stutter, that's what it says in the patent for some reason. Anyway, you react it with the methanol in the presence of KOH, and you can pull off that acetyl group, and you are left with the primary hydroxy, again, giving you, finally, sucralose. A relatively wimpy 600 times sweeter than table sugar, sucralose was invented in 1976 by British scientists. The story goes, one told the other to test the molecule, and the second scientist heard taste the molecule. So naturally, what anyone with great lab technique would do, the second scientist dabbed the sucralose and put it up in his mouth and discovered it was exceptionally sweet and not, thankfully, acutely effing toxic, and sucralose was patented shortly thereafter. In the interest of scientific integrity, if you'd like to fact-check my synthesis of sucralose back here, it's found in U.S. Patent 7884203 Bravo 2. Enjoy! Next we get to this molecule, Acesulfame Potassium, or Acesulfame K, or just ACE-K. You can see it is wicked different from anything else we were looking at, including all the fake sugars up to this point. The discovery was a broken record. Someone was in lab working with chemistry and did on the finger to flip a page in the notebook and discovered, holy cow, that stuff's wicked sweet. It's only about 200 times as sweet as table sugar, so it's just about as sweet as aspartame. But Acesulfame K has higher heat stability, so it can be used in some baking applications. The aftertaste on this guy is a little bit weird, so usually it's mixed with another fake sugar that somehow kind of synergistically creates the aftertaste effect of both of these to kind of just go away. I've paired the ACE-K with this molecule here, Saccharin, and if you look at their chemical structures, you can see why. You've got that general S double bond O coupled with the nitrogen, the ring structure. They are certainly closest to each other than they are to any of the other traditional carbohydrates, sugar alcohols, or fake sugars that we've discussed otherwise. The big difference between Saccharin and ACE-K is Saccharin has no charge on it, so it is a purely organic molecule, where the ACE-K is an ionic molecule. You have this potassium cation coupled with this polyatomic anionic structure. Saccharin's about 300 to 400 times as sweet as table sugar, so it's about twice as sweet as ACE-K or aspartame, but again, nowhere near as sweet as something like Advantame. The discovery of saccharin is, again, bad lab technique. A guy working on coal tar derivatives went home for the day and discovered at dinner that his fingers were very sweet. As it turns out, poor chemistry lab technique discovers another artificial sweetener. I will give him credit for coupling back the thought that, hey, my fingers are sweet too, maybe it was that thing I was working on in lab today, but again, demerits for not washing your hands when you go home. The synthesis of saccharin is kind of interesting to see how we get this aromatic structure coupled with this heterocycle, nitrogen, sulfur, whatever. So I'm going to wipe the board here, the ACE-K, and we can talk about how we get saccharin. The first step in the saccharin synthesis starts with toluene. We can react that with chlorosulfonic acid and we get these two ortho and para-sulfonyl chloride products. Now the para product is not really desired, so we're going to get rid of that one and just work with the ortho sulfonyl chloride. You can then react that with ammonia and you end up getting this sulfonamide. Now from this sulfonamide you can oxidize that methyl group of the toluene and you get that carboxylic acid product of that. And you'll have the sulfonamide here. What happens there is the carboxylic acid and that sulfonamide cyclizes and you're left with saccharin. There is an additional improved synthesis of saccharin that starts with a methylanthranolate, but we're not going to talk about that. Moving on. Finally, we have that sunflower plant sweetener, Stevia. It's made of two different molecules. This one is called Stevioside. The other one's actually pretty similar, but as you can see, it's a behemoth. You can kind of see some glucosey, saccharide, traditional carbohydrate looking things, but then you also have this giant three-ring dual connecting monster just smack plumb in the middle. Stevia is about, depending who you ask, a couple hundred times as sweet as table sugar, so it's about as sweet as ACE-K and aspartame, but goodness gracious, look at that. I hope you're happy. This took me like an hour and a half to draw. And that wraps up our discussion of the 7 GRAS non-nutritive sweeteners approved in the United States of America, but I do want to touch on one that is banned in the US. Sodium cyclamate. Cyclamate's about 20 to 50 times as sweet as sucrose, and it was one of the earliest artificial sweeteners used in the US. In the mid-60s, there were conflicting reports about whether this killed you or not, and in October of 1969, the Department of Education, Health and Welfare Secretary, bypassing the FDA completely, removed the GRAS designation from cyclamate, and it hasn't been back since. There were various appeals to that, but in the ensuing almost 50 years now, cyclamate is still banned in the United States. It is not, however, banned in over 130 other countries in the world, so I don't know. Of all the fake sugars out there, cyclamate has by far my favorite discovery story. Looking at the other horrible cases of lab technique, like being told to test the molecule and you tasted the molecule, or not washing your hands going home and discovering the sweetness on your fingers at dinner, cyclamate puts them all all to shame. In 1937, a graduate student at the University of Illinois was working on the benchtop, took his cigarette out of his mouth. Yes, back in those days when you were allowed to smoke in a chemistry lab with flammable solvents and I'm sure many other wonderful things. Anyway, took the cigarette out of his mouth, put it down on the benchtop, went to do something, and then when he picked the cigarette back up off the benchtop and put it back in his mouth, discovered it was sweet. And that's how Cyclamate came to be. You can see from the structure, chemically at least, Cyclamate is pretty close to Saccharin and Acesulfame K with that S double bond O with the nitrogen here. You've got the little ring here compared to the Saccharin aromatic ring. That's going to have some differences. It's an ionic compound with this sodium cation, much like Acesulfame K. So why Cyclamate is all that much different, especially considering how many countries in the world use it, I don't know, but I'm not a politician. Alright kiddos, time to get on the soapbox. Let's talk about all the dumb things that people say about artificial sweeteners. And we'll start with an easy one from sucralose. They put chlorine on my sucrose, I'm gonna die! Well, you're probably not going to die. Chlorine can be used as bad stuff, but you know what else chlorine is? Half of salt, sodium chloride. It isn't just that there are some atoms that are bad and some atoms that are good, it's what configuration the atom is in. In sucralose, the chlorines are attached covalently to carbons on that sucrose backbone. And guess what happens in your body? Basically nothing. It goes in as sucralose, it comes out as sucralose. So as far as I'm concerned, the chlorines on sucralose don't do a darn tootin' thing for you, aside from make it taste sweeter. Aspartame's the other big one. Aspartame is probably the most researched chemical from the FDA. Nothing has been more maligned than aspartame in the food additive realm. So we hear aspartame and we've got aspartic acid, we've got phenylalanine, and we've got methanol. Methanol, you say? Isn't that in wood alcohol? Doesn't that mean I'm drinking poison? No, your diet soda is probably not poisoning you. Yes, aspartame is metabolized into methanol. You know how much methanol? About that much methanol. The methanol is then converted to formaldehyde and then formic acid. The formic acid is excreted from the body faster than it can be produced, so you're never really gonna see it. Also, guess what else has methanol in it? Things like fruit juice and beer. Most any fermented beverage is going to have, you got that right, more methanol than the aspartame metabolism product from your diet cola or whatever. So hop off on the methanol. But what about phenylalanine? Isn't that bad for people with phenylketonuria? Well, yeah, absolutely. But that's like saying gluten is bad just because some people have celiac disease. Here's another one. Think about the daily recommended dose of aspartame. As it turns out, that's about 20 cans of soda. So, if you're drinking more than 20 cans of soda, maybe, just maybe, could aspartame have some maybe kind of sort of trouble for you? But that's the recommended level. If you're drinking a case of soda a day, my guess is you're going to have a few bigger problems than your aspartame metabolism. And if you don't believe me, awesome! I'm just some guy on YouTube who read a bunch of Wikipedia articles and patents and other peer-reviewed literature. Feel free to delve into the data and see what they say for yourself. Please, I beg you though, don't go on Dr. Idiot's website of scare tactics, clickbait, and fried placenta because it's probably not going to have the best recommendation for things that maybe you want to put a little bit of stock in. There are two legitimate criticisms to the whole artificial sweetener thing that I do think are worthwhile mentioning. The first is that the zero-calorie thing can make some people think that if they're pounding diet sodas all day that have no calories, that means they get to eat more calories on the back end of that. Now that's not necessarily true, and that obviously if you eat more calories just because you had no-calorie drinks, you're probably going to get fat because of that. The other one is the idea that the taste of sweetness, the sensation of sweetness, is usually associated with calorically dense foods. So if you have a taste sensation that is accompanied by no calories, you'll kind of rearrange your subconscious wires in your head, and you might get some signals crossed later in life where your body stops associating sweetness with very caloric dense stuff, which means you eat more of it, and then you get fat from there. So those two things, yeah, I would kind of buy those. And that's pretty much all I have to say about fake sugars, and for that matter, sugar alcohols and real sugars. This has been a very wild ride, and thanks for sticking with me. We'll see you next time.